Before the name Challenger became inseparable from disaster, it represented a working space shuttle and an ambitious new era of human spaceflight. Challenger was the second operational orbiter in NASA's shuttle fleet. It entered service in 1983. Over the next 3 years, it carried astronauts, satellites, scientific experiments, and equipment into orbit. Its missions included important milestones. Challenger carried the first American woman into space, Sally Ride. It carried the first African-American astronaut, Guion Bluford. It supported the first untethered spacewalk and the first shuttle mission devoted entirely to astronomy. By the beginning of 1986, Challenger had completed 9 successful flights. It was no experimental prototype. It was an established spacecraft, operating within a program that had begun to present spaceflight as increasingly regular. The shuttle was designed as a reusable orbital transportation system. Its winged orbiter carried the crew, engines, flight controls, living space, and payload bay. After completing a mission, it could return through the atmosphere and land on a runway. But the orbiter could not reach space alone. At launch, it was attached to a large external fuel tank and 2 solid rocket boosters. Together, these components formed a machine weighing more than 2,000 tons. For roughly the first 2 minutes of flight, the solid rocket boosters provided most of the thrust needed to lift the shuttle away from Earth. After burning their propellant, the boosters separated and fell toward the Atlantic Ocean. They were recovered, inspected, refurbished, and prepared for later missions. That reusability was central to the shuttle program. It was also one reason engineers had to understand how components changed after repeated manufacture, assembly, flight, recovery, and refurbishment. Inside Challenger, shuttle operations demanded constant attention. The flight deck contained the controls and displays used to guide the vehicle through launch, orbit, re-entry, and landing. From the aft section, astronauts could observe the payload bay and operate equipment during work in space. Nothing about the environment was simple. A shuttle crew had to manage propulsion, electrical power, communications, navigation, thermal control, life support, payload operations, and emergency procedures. Behind every mission stood thousands of engineers, technicians, contractors, flight controllers, and support personnel. The shuttle's apparent routine concealed an immense technical system. Success depended not only on the astronauts aboard the orbiter, but on every component performing within its limits. Each flight brought together people with specialized roles. Commanders and pilots operated the spacecraft. Mission specialists managed experiments, satellites, spacewalks, and other technical tasks. Payload specialists sometimes joined crews to support a particular scientific or commercial objective. They trained together for months. They rehearsed normal operations and emergency procedures. They learned the spacecraft, the mission timeline, and one another's responsibilities. By 1986, shuttle flights had become major public events, but they were no longer treated as rare national spectacles in the way the earliest crewed launches had been. NASA was working toward a demanding flight schedule. Behind that schedule was a launch system, whose most powerful components were the 2 solid rocket boosters. A solid rocket booster operates differently from a liquid fuel engine. Its propellant is manufactured as a solid material and packed inside a steel casing. Once ignited, it burns continuously. It cannot be throttled down or switched off. The shuttle's boosters were enormous. Each stood about 45 meters tall and contained several hundred tons of propellant. At liftoff, They burned with enough combined force to help accelerate the entire shuttle stack upward. The boosters had to withstand extreme pressure, vibration, heat, and structural load. Their steel casings also had to be transportable. They were therefore built in separate cylindrical sections. Those sections were manufactured in Utah, transported to the Kennedy Space Center in Florida, and assembled into complete boosters before launch. The connections between them were known as field joints. Each field joint joined the lower end of one booster segment to the upper end of another. One section contained a projecting metal tongue. The adjoining section contained a matching clevis. When assembled, the tongue fitted between the clevis walls, and large steel pins locked the sections together. Inside the joint were two rubber seals known as O-rings. The primary O-ring was intended to prevent hot combustion gas from escaping. The secondary O-ring provided an additional barrier. When the booster ignited, internal pressure rose rapidly. The steel casing expanded slightly under the load. That movement mattered. As the joint changed shape, the O-rings had to respond quickly enough to remain in contact with the sealing surfaces. If a gap opened before a ring moved into position, superheated gas could penetrate the joint. The entire launch vehicle depended on those seals working within fractions of a second. The boosters had undergone full-scale testing during development. Static firings allowed engineers to ignite complete motors while holding them on the ground. Instruments measured pressure, temperature, thrust, vibration, and structural behavior. The tests demonstrated the extraordinary power of the system. They also helped qualify the booster for crewed flight. But testing could not reproduce every combination of manufacturing variation, refurbishment history, temperature, and launch condition. As shuttle operations continued, engineers accumulated evidence from actual missions. After several flights, inspections found signs that hot gas had reached parts of some field joints. In certain cases, primary O-rings showed erosion. In others, heat had affected the putty placed inside the joint. The seals had not always behaved as designers originally expected. Yet because the secondary O-ring had remained intact, the booster system continued to be judged flight-worthy. An O-ring is a simple object. It is a circular loop of elastic material. When compressed inside a groove, it presses against surrounding surfaces and closes the path through which gas or liquid might escape. Its effectiveness depends on flexibility. When pressure changes or connected parts move, the ring must change shape and maintain contact. In the shuttle booster joint, the rings were made from a synthetic rubber known as Vitin. Like many elastic materials, Vitin becomes less flexible as its temperature falls. A warm O-ring can recover its shape quickly after being compressed. A colder ring responds more slowly. That difference can be measured in fractions of a second. Inside an igniting rocket motor, fractions of a second can determine whether a seal closes a gap before hot gas enters it. The danger was connected to a phenomenon engineers called joint rotation. When booster pressure increased, the walls of the clevis could bend outward slightly. This movement could enlarge the space that the O-ring was meant to seal. To work correctly, the primary ring had to move across that opening as it developed. The motor's internal pressure was expected to push the ring into place. But pressure could help only after it reached the ring. Before that happened, the material had to respond to the changing joint. If the ring was stiff, delayed, or held away from the sealing surface, hot combustion gas could begin moving through the gap. Once that gas created a path, It could burn the rubber seal and attack the surrounding metal. The joint contained a backup ring, but joint rotation could also reduce the secondary ring's ability to seal. The design therefore contained redundancy, but not complete independence. Evidence of abnormal O-ring behavior had appeared years before Challenger's final flight. In 1981, engineers identified erosion on a primary O-ring after the second shuttle mission. Further cases followed. The amount of damage varied. Sometimes the ring was only lightly affected. On other flights, the evidence was more serious. Engineers studied changes to the joint and to the insulating putty placed between the propellant and the O-rings. NASA and the booster contractor, Morton Thiokol, continued to analyze the problem, but the shuttle continued flying. Past success became part of the reasoning. Each time a damaged seal was discovered after a safe mission, the incident provided evidence of a problem. It also appeared to demonstrate that the system could tolerate that problem. The absence of catastrophe was gradually treated as evidence of an acceptable safety margin. Temperature became an increasingly important concern. In January 1985, Shuttle Mission 51C launched in unusually cold weather. After recovery, engineers found severe erosion on both primary O-rings in one booster joint. Hot gas had passed the first seal and affected the second. The launch day air temperature had been about 12 degrees Celsius. The joint itself may have been colder. Roger Boisjali, an engineer at Morton Thiokol, regarded the findings as a warning. He and other engineers argued that colder O-rings could take longer to move into a sealing position. Boisjali warned that the result could be catastrophic if both seals failed to contain the motor's gases. During 1985, Morton Thiokol and NASA discussed possible redesigns. The existing joints were still being used. The problem was known. Its precise relationship with temperature was not fully quantified, and no rule prohibited launching below a specific temperature. By January 1986, the technical history of the booster joints contained two competing narratives. One was reassuring. The shuttle had flown repeatedly. O-ring damage had been observed, but no booster had failed. Engineers had introduced inspections and modifications, and previous missions had returned safely. The other narrative was more troubling. The primary seals had eroded. Hot gas had sometimes reached the secondary seals. Joint movement was greater than originally expected. Cold rubber responded more slowly, and the most serious recorded damage had followed the coldest shuttle launch so far. On Challenger's next mission, the aft field joint of the right solid rocket booster would be exposed to temperatures lower than any in the program's flight history. The consequences would depend on a pair of rubber rings, each less than a centimeter thick, sealing a motor filled with burning propellant. But STS-51L would not be remembered only as an engineering failure. It was also the shuttle mission that NASA had chosen to carry a teacher into space. In 1984, President Ronald Reagan announced a program intended to bring the experience of spaceflight into American classrooms. NASA would select a teacher to fly aboard a shuttle, conduct lessons from orbit, and return to share that experience with students across the country. The Teacher in Space project reflected a broader effort to make the shuttle program more accessible to the public. More than 11,000 teachers applied. The selection process examined their professional experience, communication skills, physical readiness, and ability to translate a complex space mission into something students could understand. On July 19, 1985, Vice President George H.W. Bush announced the final choice at the White House. The primary participant was Krista McAuliffe, a social studies teacher from Concord, New Hampshire. Her backup was Barbara Morgan, an elementary school teacher from Idaho. McAuliffe and Morgan entered the program together. Morgan would complete much of the same preparation and would be ready to take McAuliffe's place if necessary. Both women were experienced educators, but neither was a professional astronaut. Their role was different from that of the career crew members. They were not being trained to command or pilot the shuttle. They were preparing to live and work aboard it safely, assist with assigned tasks, and carry out educational activities from orbit. McAuliffe planned 2 televised lessons. One would introduce students to the shuttle and explain how astronauts lived in microgravity. The other would describe the flight and preparation of a shuttle mission. Additional demonstrations would examine subjects such as motion, magnetism, liquids, and the behavior of simple objects in weightlessness. The lessons were intended to turn Challenger into a classroom beyond Earth. Preparing for that role required more than writing lesson plans. McAuliffe and Morgan learned to operate cameras and other equipment that would be used to record activities aboard the shuttle. They studied the mission schedule and practiced procedures inside shuttle trainers. Every activity in orbit had to be planned around the demands of the spacecraft. Time, electrical power, communications, storage space, and crew attention were limited. Even a short classroom demonstration had to be tested, packed, secured, and integrated into the mission timeline. Objects that remain still on Earth can drift away in microgravity. Liquids do not pour normally. Equipment must be restrained, and each movement must account for the confined cabin around it. The educational program, therefore, depended on the same careful preparation required for every other shuttle payload. Training also introduced McAuliffe to the physical environment of astronaut operations. Flights in NASA's T-38 aircraft exposed participants to rapid acceleration, steep climbs, banking turns, radio procedures, and the disciplined routines used by flight crews. The aircraft could not reproduce a shuttle launch, but it offered experience in a fast-moving cockpit where instructions had to be understood and followed immediately. McAuliffe also flew aboard an aircraft that created brief periods of weightlessness by following a series of parabolic arcs. During each descent, the people inside floated for only a short time before gravity returned. These flights allowed her to rehearse movements and demonstrations that would later be performed in orbit. They also revealed how ordinary actions changed when there was no floor beneath the body and no stable surface on which to place an object. At the Johnson Space Center in Houston, McAuliffe trained alongside the astronauts assigned to STS-51L. She learned the location of emergency equipment, the use of breathing apparatus, and the procedures for entering and leaving the spacecraft. She practiced communications and became familiar with the shuttle's middeck, where she would spend much of the mission. The middeck contained crew seating, storage compartments, sleeping arrangements, food equipment, and the airlock hatch. During launch and landing, McAuliffe would be secured in a seat below the flight deck. Once in orbit, the same compact area would become a workplace, dining space, sleeping area, and classroom. Her preparation was abbreviated compared with the training of career astronauts, but it was not symbolic. NASA expected her to understand the spacecraft, follow procedures, and function as part of the crew. That preparation included the most ordinary details of living away from Earth. Food was packaged so that it could be stored safely, prepared with limited equipment, and eaten without loose fragments floating into switches or ventilation systems. Some items were dehydrated and required water. Others were ready to eat. Containers, utensils, and waste all had to be managed within the shuttle's closed environment. These practical routines helped McAuliffe explain spaceflight in recognizable terms. The Teacher in Space project was built around that connection. Students might not immediately understand orbital mechanics or propulsion systems. They could understand questions about eating, sleeping, washing, moving, and working. By answering those questions from orbit, McAuliffe was meant to make human spaceflight feel less distant. Her participation also brought unusual attention to the mission. Schools across the United States prepared to watch the launch and the planned lessons. Sharon Krista Corrigan McAuliffe was 37 years old. She taught social studies at Concord High School and had previously worked in schools in Maryland and New Hampshire. Her subjects included American history, economics, law, and a course examining the role of women in American history. She was married to Stephen McAuliffe and had 2 children. Colleagues and students knew her as a teacher who connected historical events with the lives of ordinary people. That approach suited the purpose of the NASA program. McAuliffe was not presented as someone separate from the public. Her significance came from being part of it. She was a teacher, parent, and community member who had been selected to enter an environment previously reserved for highly specialized astronauts and researchers. For NASA, that made her an effective ambassador. For the public, it made the mission unusually personal. The flight was designated STS-51L. Its primary payload was a tracking and data relay satellite, which was intended to strengthen communications between spacecraft and ground stations. The mission also carried the Spartan Halley spacecraft. Once released from Challenger, Spartan was expected to observe Halley's comet before being retrieved and returned to Earth. McAuliffe's lessons formed one part of a wider mission involving satellite deployment, scientific observation, and shuttle operations. The official mission patch represented the 7 crew members through 7 stars. It also depicted Challenger rising from Florida toward space. By launch day, STS-51L had attracted an audience far larger than most recent shuttle missions. The presence of a school teacher meant that classrooms would be watching alongside engineers, journalists, government officials, and the families of the crew. Commander Francis Scobie was making his second journey into space. Pilot Michael Smith was preparing for his first. Mission specialist Ellison Onizuka had previously flown aboard the shuttle Discovery. Judith Resnick had also completed one earlier mission. Ronald McNair was a physicist and an experienced astronaut who had flown aboard Challenger in 1984. Payload specialist Gregory Jarvis was an engineer from Hughes Aircraft. He was assigned to conduct experiments involving the behavior of fluids in microgravity. Krista McAuliffe was the second payload specialist. Together, the 7 formed a crew with different backgrounds and responsibilities. 5 were NASA astronauts. Jarvis represented the commercial payload program. McAuliffe represented the Teacher in Space project. Their mission was expected to last nearly 7 days. During that time, they would deploy satellites, conduct experiments, document shuttle operations, and deliver educational broadcasts to Earth. Before flight, the crew rehearsed how to leave the shuttle during an emergency on the launch pad. They practiced opening the side hatch, crossing the access arm, and reaching evacuation equipment. These exercises addressed dangers that might arise before liftoff, while the orbiter was still connected to the launch tower. Once the solid rocket boosters ignited, the situation changed completely. The boosters could not be shut down. The shuttle had to continue flying until they exhausted their propellant and separated. The crew had no escape system capable of carrying 7 people away from the vehicle during the first stage of ascent. Their survival, therefore, depended on the launch vehicle remaining intact. The astronauts understood that spaceflight involved risk, but they entered Challenger expecting that the spacecraft and its systems had been judged ready to fly. As the planned launch approached, the crew completed its training. In Florida, Challenger stood at Launch Pad 39B. The mission had already been delayed several times. Then a mass of Arctic air moved across the state, bringing the Kennedy Space Center its coldest conditions of the shuttle era. Launch day was Tuesday, January 28, 1986. The crew woke before dawn and followed the routine that had preceded every shuttle mission. Medical checks were completed, weather briefings were reviewed, breakfast was served. Outside, however, conditions were unlike any previously experienced during a shuttle launch. An intense cold front had settled across central Florida. During the night, temperatures fell well below freezing. Ice formed on launch structures, service towers, and support equipment throughout the Kennedy Space Center. For engineers responsible for the launch pad, the ice presented an immediate operational concern. Large pieces could break loose during ignition, strike the orbiter, damage delicate thermal protection tiles, or interfere with critical systems. Before sunrise, inspection teams moved across the launch complex to assess the extent of the ice accumulation. The launch schedule was delayed while photographs were taken, and engineers evaluated whether Challenger could safely leave the pad. The cold itself was becoming a subject of discussion, not only because of ice, but because the shuttle's solid rocket booster joints had never before been launched after such low overnight temperatures. Standing on Launch Pad 39B, Challenger appeared unchanged. The orbiter was attached to its orange external tank and flanked by 2 towering white solid rocket boosters. Together, they formed one of the most powerful launch vehicles ever built. Yet appearance revealed very little. The external tank contained millions of liters of cryogenic liquid hydrogen and liquid oxygen. The boosters held hundreds of tons of solid propellant. Within the steel joints connecting each booster segment, the rubber O-rings had spent hours exposed to temperatures significantly lower than those experienced during previous shuttle launches. Engineers understood that the metal structure, insulation, seals, and support hardware would all respond differently as temperatures changed. Exactly how those conditions would affect the booster joints during ignition remained uncertain. The launch vehicle waited while discussions continued. Those discussions had begun the previous evening. On January 27th, engineers from Morton Thiokol and NASA held a lengthy teleconference to review the unusually cold forecast. Among the most vocal participants was Roger Boisjali. Drawing upon previous flight data, he argued that the solid rocket boosters should not be launched under conditions colder than any previously experienced. He warned that low temperatures could delay the movement of the primary O-ring. If that happened, Hot combustion gases might pass the seal before it had fully seated. Other engineers shared similar concerns. Initially, Morton Thiokol management recommended against launching. NASA managers questioned the evidence supporting that recommendation. They asked whether the available data demonstrated that launch would be unsafe. The discussion continued for several hours. After an internal management meeting, Morton Thiokol reversed its position. The company recommended proceeding with the launch. NASA accepted that recommendation. The decision would later become one of the most closely examined aspects of the Challenger investigation. By mid-morning, ice inspections had concluded. Engineers determined that although significant ice remained around parts of the launch complex, Challenger itself could proceed. The countdown resumed. At 11:38 in the morning, Eastern Standard Time, the three main engines ignited. Moments later, the two solid rocket boosters came to life. Explosive bolts released the shuttle from the launch pad. Nearly 7 million pounds of thrust lifted Challenger slowly upward. As the vehicle cleared the tower, it rolled onto its planned flight path over the Atlantic Ocean. To spectators, the launch appeared completely normal. Millions of television viewers watched from homes, schools, and workplaces. Children across the United States expected to see the first teacher travel into space. None could see what was happening inside the aft field joint of the right solid rocket booster. Within seconds of liftoff, cameras recorded small puffs of dark smoke emerging from the aft field joint of the right booster. The smoke appeared between roughly half a second and just under 3 seconds after ignition. It lasted only briefly. As internal pressure increased, combustion products and molten material sealed the opening. For much of the first minute of flight, the temporary seal appeared to hold. Challenger continued climbing normally. The shuttle accelerated through increasing aerodynamic forces as it approached the period known as maximum dynamic pressure, or max-Q. The crew reported that everything was proceeding as expected. Mission Control continued receiving normal telemetry. Nothing suggested an immediate emergency. But conditions around the booster were changing. As Challenger climbed, powerful upper-level winds caused the vehicle to flex and respond to changing aerodynamic loads. Investigators would later conclude that these changing forces affected the temporary seal inside the right booster joint. At approximately 58 seconds after liftoff, cameras revealed a bright flame emerging from the right booster. The temporary seal had failed. Hot combustion gases escaped through the damaged field joint. The flame was directed toward the large external tank positioned beside the booster. As Challenger continued accelerating, the escaping jet burned into the metal support connecting the booster to the tank. It also weakened the wall of the liquid hydrogen tank itself. For several seconds, the shuttle continued flying. From the ground, nothing appeared dramatically different. Inside Mission Control, telemetry still flowed from the spacecraft. But structural damage was increasing rapidly. The right booster was no longer fully restrained by its forward and aft attachments. The escaping flame was progressively destroying the structure that held the launch vehicle together. 73 seconds after liftoff, the weakened structure could no longer withstand the forces acting upon it. The attachment between the right booster and the external tank failed. The booster pivoted outward. Its nose struck the external tank. The liquid hydrogen tank ruptured. Liquid hydrogen and liquid oxygen mixed violently as the vehicle broke apart under overwhelming aerodynamic loads. The large white cloud seen by millions of viewers was not a conventional explosion. It was the rapid destruction of the launch vehicle as propellants escaped and burned. The orbiter, external tank and boosters separated into multiple pieces. The two solid rocket boosters, still producing thrust, continued flying independently until range safety officers destroyed them. On the ground, observers struggled to understand what they had witnessed. Inside Mission Control, controllers searched for data that never returned. The mission had ended. Immediately after the breakup, Mission Control attempted to re-establish communications. Controllers called Challenger repeatedly. No response came. Telemetry disappeared from their displays. Flight Director Jay Green and his team began following contingency procedures. Across the Atlantic Ocean east of Florida, ships, aircraft, and rescue personnel were directed toward the debris field. As additional information arrived, it became increasingly clear that Challenger had been lost. The shuttle program stopped immediately. Scheduled launches were suspended. Across the United States, television networks interrupted regular programming. Millions who had watched the launch now watched the first reports of the disaster. For many schoolchildren, it was the first time they had witnessed a national tragedy unfold live. NASA now faced two responsibilities. One was recovery. The other was understanding exactly why the accident had happened. That evening, President Ronald Reagan addressed the nation from the Oval Office. The scheduled State of the Union address was postponed. Instead, the president spoke directly about the loss of Challenger and its 7 crew members. He expressed sympathy for the families, praised the astronauts' courage, and reminded viewers that exploration had always involved risk. The address became one of the defining public responses to the disaster. Across the country, flags were lowered. Schools canceled planned celebrations connected with the teacher and space mission. NASA employees, contractors, astronauts, and support staff confronted the reality that the shuttle program had suffered its first fatal in-flight accident. The nation mourned. But even as memorial preparations began, investigators were already gathering evidence that would reshape the future of American human spaceflight. 3 days later, on January 31st, 1986, a national memorial service was held at the Lyndon B. Johnson Space Center in Houston. President Reagan attended alongside government officials, NASA leaders, astronauts, and the families of the crew. Each of the 7 astronauts was remembered individually. The ceremony acknowledged not only their professional achievements, but also the families and communities left behind. For NASA, the memorial marked the end of one chapter. The search for answers was only beginning. The wreckage lay scattered across a wide area of the Atlantic Ocean. Some of the most important evidence had yet to be recovered. The investigation that followed would examine engineering decisions, management culture, communication failures, and the assumptions that had developed during years of successful shuttle operations. Those findings would permanently change the American space program. The days following the disaster brought public mourning across the United States. Families of the 7 crew members gathered alongside astronauts, NASA officials, government leaders, and thousands of mourners. Behind every photograph of the memorial stood lives interrupted. Francis Scobie had commanded only his second space mission. Michael Smith had been making his first journey into orbit. Ellison Onizuka had become the first Asian-American astronaut to fly in space. Judith Resnick was one of NASA's most accomplished engineers. Ronald McNair was a physicist whose research and determination had carried him from rural South Carolina to the astronaut corps. Gregory Jarvis had waited years for an opportunity to fly. Krista McAuliffe had prepared to teach millions of students from orbit. Their deaths transformed the Challenger disaster from a technical failure into a deeply personal national tragedy. Within NASA, the loss was profound. Astronauts trained together for years. They relied upon one another professionally and often developed close personal friendships. The disaster affected flight crews, instructors, engineers, technicians, flight controllers, and support staff throughout the agency. For many employees, Challenger challenged long-held confidence in the Shuttle program. NASA had experienced setbacks before. Apollo 1 had claimed the lives of 3 astronauts during a ground test in 1967. But Challenger was different. It unfolded live before a worldwide audience. Millions watched it happen. The agency now faced intense public scrutiny, while also confronting painful questions from within. How had known engineering concerns failed to prevent launch? And what needed to change before astronauts could fly again? Recovery operations began almost immediately. The search area stretched across hundreds of square miles of the Atlantic Ocean, east of Cape Canaveral. The United States Coast Guard, the United States Navy, NASA, and numerous civilian organizations participated in one of the largest recovery efforts in American history. Ships, helicopters, fixed-wing aircraft, sonar systems, remotely operated equipment, and divers all contributed to the search. The work continued for months. Weather, sea conditions, and water depth made recovery difficult. Every recovered component offered investigators another piece of evidence. Nothing was considered too small to examine. The objective was not simply to recover debris. It was to reconstruct the sequence of events that had destroyed Challenger. Among the recovered material were components from the mission's payloads. The tracking and data relay satellite, which Challenger had been carrying into orbit, never reached space. Fragments of scientific equipment, structural components, insulation, electronics, and payload hardware were cataloged and examined. Every item was photographed. Its recovery location was recorded. Investigators compared damage patterns across thousands of individual pieces. The physical evidence complemented launch photography, telemetry, engineering drawings, manufacturing records, and previous flight data. Each source answered part of the story. None could answer every question alone. Understanding the accident required combining all of them. Recovered shuttle components were transported to secure facilities for examination. Investigators organized debris according to its original location within the vehicle. Gradually, sections of Challenger were reconstructed on the ground. This process allowed engineers to distinguish damage caused during the breakup from damage that had occurred beforehand. Patterns became visible. Burn marks, fractures, missing material, and deformed metal revealed how forces had traveled through the launch vehicle. The reconstruction supported conclusions already suggested by launch photography. Attention increasingly focused upon the aft field joint of the right solid rocket booster. There, investigators believed the accident had begun. The wreckage alone did not explain everything. Investigators also examined engineering reports, internal memoranda, certification records, launch procedures, meeting notes, and testimony from NASA and contractor personnel. This broader investigation revealed that concerns about O-ring performance had existed long before Challenger launched. Engineers had documented erosion. They had debated possible causes. They had proposed redesigns. Yet shuttle flights had continued. No single document explained the disaster. Instead, investigators found a chain of technical issues, communication problems, management decisions, and organizational assumptions that combined over time. Understanding Challenger required examining not only failed hardware, but also the process by which that hardware had continued flying. On February 3, 1986, President Reagan established the Presidential Commission on the Space Shuttle Challenger accident. It became widely known as the Rogers Commission after its chairman, former Secretary of State William P. Rogers. Its members included former astronaut Neil Armstrong, test pilot Chuck Yeager, physicist Richard Feynman, astronaut Sally Ride, and specialists from engineering, science, defense, and public service. The commission examined launch records, engineering analyses, internal correspondence, and testimony from dozens of witnesses. Its investigation reached two closely connected conclusions. Technically, the accident began when the primary O-ring in the aft field joint of the right solid rocket booster failed to seal properly under unusually cold launch conditions. Hot combustion gases escaped through the joint. The resulting flame damaged the external tank and weakened the structural attachment between the booster and the tank until the launch vehicle broke apart. But the commission concluded that the technical failure alone did not explain the disaster. Management processes had also failed. Information about O-ring concerns had not been communicated effectively through NASA's decision-making structure. Engineering uncertainty had been interpreted as evidence that launching remained acceptable. Previous missions had experienced O-ring erosion without catastrophic consequences. Instead of prompting increasingly cautious decisions, repeated success gradually reduced the perceived seriousness of the warning signs. The commission criticized this process directly. It concluded that NASA's organizational culture had contributed to the accident, alongside the engineering failure itself. The report recommended redesigning the booster joints, strengthening safety oversight, improving communication between engineers and managers, and changing the way launch decisions were evaluated. Those recommendations reshaped the shuttle program. Human spaceflight would not resume for more than 2.5 years. One visible reminder of Challenger survives today. A large section of the recovered orbiter is preserved at the Kennedy Space Center Visitor Complex. The displayed structure bears the marks of the recovery effort rather than restoration. It stands not as a reconstructed spacecraft, but as physical evidence of the mission that was lost. For visitors, the fragment bridges the distance between historical photographs and the reality of the accident. It reminds observers that Challenger was not simply a symbol. It was a spacecraft built by thousands of people, flown by 7 astronauts, and lost during a mission that permanently changed the history of space exploration. The investigation explained how the accident happened. Its legacy would be defined by what was learned from it. The Challenger disaster did not end with the publication of the Rogers Commission report. Its findings changed the direction of the American space program. Engineers redesigned the solid rocket booster joints to provide a more reliable seal under a wider range of operating conditions. Independent safety oversight was strengthened. Launch decision processes became more formal, placing greater emphasis on documenting uncertainty, rather than assuming that previous success guaranteed future safety. NASA also reconsidered the pace of shuttle operations. Before Challenger, ambitious launch schedules had encouraged the belief that spaceflight was becoming increasingly routine. The accident demonstrated that routine appearance could never eliminate technical risk. Every launch remained an engineering experiment involving thousands of interconnected systems. The 7 crew members became remembered not only for the mission they attempted, but for the changes their loss ultimately brought to human spaceflight. Permanent memorials were established across the United States. Among the most prominent is the Space Shuttle Challenger Memorial at Arlington National Cemetery. The memorial honors all 7 members of the crew together. Unlike temporary ceremonies held in the days after the disaster, permanent memorials allow later generations to encounter Challenger as part of history rather than current events. Visitors arrive decades after the launch. Many were not yet born in 1986. Yet the memorial continues to tell the same story. Exploration carries extraordinary rewards. It also carries responsibility. Remembering those who accepted that responsibility remains an essential part of understanding the history of spaceflight. The crew is also remembered individually. Ellison Onizuka's career represented years of determination, technical achievement, and public service. After earning degrees in aerospace engineering, he joined the United States Air Force before being selected as a NASA astronaut. In 1985, he became the first Asian American to travel into space. His second mission was Challenger. Schools, scholarships, observatories, roads, research facilities, and public buildings now bear his name. For many communities, these memorials preserve not only the memory of the accident, but the example of a life devoted to science, engineering, and exploration. Krista McAuliffe's legacy followed a different path. She entered the mission not as a career astronaut, but as a classroom teacher chosen to share spaceflight with students. Although the lessons planned for orbit were never delivered, her educational mission continued in another form. Schools, libraries, scholarships, learning centers, and educational foundations were established in her name. Teachers across the United States have continued using her story to encourage curiosity, resilience, and public service. The Teacher in Space project ended with Challenger, but the idea that education should remain closely connected with exploration survived. In that sense, McAuliffe's influence extended well beyond the mission itself. Museums and educational institutions preserve artifacts connected with Krista McAuliffe and the Challenger mission. These exhibits do more than display historical objects. They explain the broader context of the shuttle era. Visitors learn how astronauts trained. They examine mission equipment, photographs, documents, and personal items. They also encounter the engineering lessons that emerged from the investigation. The story presented is not one of failure alone. It is also a story of learning. engineering advances through careful examination of mistakes as well as successes. That principle lies at the heart of aerospace safety. Remembrance extends beyond NASA itself. Military organizations, educational institutions, scientific communities, museums, and civic groups continue holding ceremonies that honor the Challenger crew. Each commemoration reflects a shared understanding. The astronauts accepted extraordinary risk in pursuit of knowledge, exploration, and public service. Their work belonged not only to NASA, but to a wider human effort to understand and explore beyond Earth. The disaster, therefore, occupies a unique place in public memory. It is remembered both as a national tragedy and as an event that transformed engineering practice. The connection between Challenger and later spaceflight has remained visible. Decades after the accident, astronauts aboard the International Space Station carried remembrance objects linked to the Challenger crew. These gestures reflected continuity rather than closure. Human spaceflight continued. The International Space Station became the largest permanent human presence ever established in orbit. New spacecraft replaced the Shuttle. New generations of astronauts entered service. Yet Challenger remained part of their professional history. Every mission carried forward lessons first written in the investigation that followed January 20th, 1986. Today, Challenger is remembered for two parallel histories. The first is the story of 7 individuals who prepared for a mission they believed was ready to fly. Francis Scobie, Michael Smith, Ellison Onizuka, Judith Resnick, Ronald McNair, Gregory Jarvis, and Krista McAuliffe. The second is the story of an engineering system that failed because technical warnings, organizational decisions, and management assumptions combined under conditions that had not been adequately understood. Neither history is complete without the other. The Challenger disaster demonstrated that exploration demands more than courage. It requires constant questioning, careful engineering, transparent communication, and the willingness to confront uncertainty before lives depend upon the answers. Those lessons remain as relevant today as they were in 1986. They continue to shape the way humanity prepares for every journey beyond Earth. The mission lasted only 73 seconds. Its influence continues decades later. The Challenger disaster occupies a singular place in the history of human spaceflight. It was not the first fatal accident in the American space program, but it was the first to unfold before a live television audience that stretched across an entire nation. For millions of people, especially schoolchildren expecting to watch Krista McAuliffe begin her lessons from orbit, the launch became an unforgettable moment. For engineers, it became a permanent reminder that successful missions cannot erase unresolved technical concerns. The Rogers Commission concluded that Challenger was not the result of a single mistake. The accident emerged from the interaction of engineering limitations, organizational decisions, communication failures, and the gradual acceptance of known risks. Those conclusions continue to influence aerospace engineering today. Launch vehicles are examined with greater independence. Safety organizations are given stronger authority. Engineers are encouraged to raise concerns without fear that schedule or institutional pressure will outweigh technical evidence. Every major spacefaring nation now incorporates lessons that echo those learned after Challenger. The legacy of the mission, therefore, extends far beyond NASA. It has shaped spacecraft design, launch certification, risk management, systems engineering, and the culture of safety throughout the aerospace industry. The 7 members of the crew are remembered individually. Francis Richard Scobie, Michael John Smith, Ellison Shoji Onizuka, Judith Arlene Resnick, Ronald Irwin McNair, Gregory Bruce Jarvis, and Sharon Krista McAuliffe. Each accepted the risks of exploration in pursuit of scientific discovery, public service, and the expansion of human knowledge. Their mission lasted 73 seconds. Its lessons have endured for decades. Today, every successful launch carries with it the accumulated experience of those who flew before. Every countdown reflects thousands of engineering decisions. Every launch commit decision depends upon evidence, careful review, and the willingness to stop when uncertainty cannot be resolved. That may be Challenger's most enduring contribution. Not simply the memory of a tragedy, but the understanding that progress in exploration depends upon learning honestly from failure. The story of Challenger is therefore not only about how 7 lives were lost. It is also about how their loss changed the practice of human spaceflight. As long as people continue reaching beyond Earth, the lessons of January 28, 1986, will remain part of every journey. The mission ended. The responsibility to remember, to learn, and to improve continues. End credits. The Challenger disaster marked the end of one chapter in the history of human spaceflight. It also marked the beginning of another. The investigation that followed transformed spacecraft engineering, launch decision-making, and the culture of safety within NASA and across the aerospace industry. The redesigned solid rocket boosters first flew when the Space Shuttle program resumed with STS-26 on September 29, 1988. The shuttle fleet would continue flying for more than 2 decades. Yet every mission after Challenger carried the weight of lessons learned in 1986. The names of the 7 crew members remain permanently associated with courage, service, and exploration. Francis Richard Scobie, Michael John Smith, Ellison Shoji Onizuka, Judith Arlene Resnick, Ronald Irwin McNair, Gregory Bruce Jarvis, and Sharon Krista McAuliffe. Their legacy lives not only in memorials and museums, but in every engineering review, every launch readiness assessment, and every decision to place safety above schedule. History remembers Challenger as a tragedy. Engineering remembers it as a warning. Exploration remembers it as a responsibility. The pursuit of knowledge has always required courage. Its future depends equally upon humility, evidence, and the willingness to learn. Thank you for watching.